Welcome! In this session, we'll dive into LeetCode problem number 1578, minimum time to make rope colorful. This problem challenges us to optimize the time required to make a rope colorful while adhering to specific conditions. Let's explore the solution together. Alice has a rope with n balloons hanging in a row, where each balloon is represented by a character in the string colors. The goal is to make this rope colorful, meaning no two adjacent balloons can have the same color. However, if there are adjacent balloons with the same color, Alice can remove one or more balloons to break this pattern. The time it takes to remove the ith balloon is given by the integer array needed time. Our task is to determine the minimum time required to make the rope colorful. To better understand the problem, consider the first example. Here, colors is given as a back and needed time as 1, 2, 3, 4, 5. To make the rope colorful, Alice removes the balloon at index 2, which has the color at and a removal cost of 3. This results in the rope A back, where no two adjacent balloons share the same color. The total cost is 3. In the second example, colors is ABC and needed time is 1, 2, 3. Since the rope is already colorful, no balloons need to be removed, and the total cost is 0. In another example, colors is ABA and needed time is 1, 2, 3, 4, 1. Here, Alice needs to remove 2 balloons to make the rope colorful. She can remove the balloon at index 0 or 4, both of which are with a removal cost of 1. Additionally, she removes the balloon at index 1, which is also with a cost of 1. This results in the rope ABA, which is colorful, and the total cost is 1 plus 1 is equal to 2. The problem also comes with constraints to ensure the solution handles inputs efficiently, such as colors.length being equal to needed time.length and both being as large as 10 to the power of 5. There are a few edge cases to consider. If there are no adjacent balloons with the same color, the output is 0, as no removals are necessary. For a single balloon, the rope is already colorful, so the cost is also 0. On the other hand, if all balloons have the same color, Alice must remove all but one of them. In this case, the cost will be the sum of all needed time values except the largest one. Finally, the solution must handle large inputs efficiently, where n can go up to 10 to the power of 5 and needed time, I, can reach values close to 10 to the power of 4, ensuring the program runs within time and space constraints. To tackle the problem of minimizing the total time required to make the rope colorful, we need to ensure that no two adjacent balloons share the same color. Each balloon has an associated removal cost, given in the needed time array. The challenge is to remove balloons with the goal of resolving adjacent duplicates while minimizing the total removal cost. One approach we could consider is the brute force method. Here, the idea is to iteratively traverse the string of colors and identify groups of adjacent duplicates. For each group, we remove balloons until only one remains, always prioritizing the removal of the least costly balloons. While this method is simple to understand and implement, it involves repeated traversal of the string, resulting in a time complexity of n squared. This makes it inefficient for larger inputs. On the other hand, we can consider a more optimized approach. Instead of repeated traversals, we resolve duplicates as we encounter them during a single traversal of the string. By maintaining a running sum of removal costs for each group of duplicates and keeping track of the maximum cost within the group, we can minimize the removal cost while preserving one balloon in each group. In the optimized approach, we subtract the maximum cost from the total group cost, ensuring that only the most expensive balloon in the group remains. This is achieved through a single traversal using 2 indices, one to track the current balloon and another to keep track of the previous balloon. With this approach, the time complexity is reduced to n, as the string and the needed time array are traversed only once. Additionally, the space complexity remains 1, as no extra data structures are required beyond simple counters. This method is not only efficient but also avoids unnecessary operations, making it suitable for handling large inputs. After evaluating both approaches, we chose the optimized solution for its efficiency and simplicity. The algorithm scales well for large cases, such as when there are up to 10 to the power of 5 balloons. Moreover, the implementation remains straightforward, avoiding the complexity of nested loops or additional data structures. The key observation here is that within any group of adjacent duplicates, only one balloon needs to remain. By keeping the balloon with the highest removal cost and removing the others, we achieve the minimum total cost while meeting the problem's requirements. The core insight that drives the optimized approach is recognizing that within any group of adjacent duplicates, the optimal strategy is to keep only the balloon with the highest removal cost and eliminate the rest. This realization eliminates the need for repeated traversals or additional computations, as we can resolve each group during a single pass through the string. When comparing the two approaches, the brute force method is intuitive but inefficient due to redundant operations. The optimized approach, in contrast, is both concise and highly efficient, making it ideal for scenarios like competitive programming where performance matters. Alternative strategies, such as sorting the balloons based on removal costs, are unnecessary and less effective for this specific problem. Ultimately, the optimized approach strikes the perfect balance between clarity and performance. It minimizes the total removal cost in an elegant and computationally efficient manner, making it the best solution to the problem of minimizing the time required to make the rope colorful. The problem minimum time to make rope colorful focuses on minimizing the time required to make a rope visually appealing. Here, the rope is represented as a sequence of balloons, each associated with a color and a removal cost. The key requirement is that no two adjacent balloons can share the same color. To achieve this, if two or more consecutive balloons have the same color, we must remove some of them, incurring their respective removal costs. The aim is to minimize this overall cost while ensuring that adjacent balloons have distinct colors. To solve this, we employ a greedy algorithm. First, we initialize variables, total time to store the cumulative removal cost and a pointer I to iterate over the string of colors. Then, as we traverse the rope, we identify groups of consecutive balloons with the same color and calculate their associated costs. This setup allows us to systematically address the problem with minimal computational overhead. Once groups of balloons with the same color are identified, we process each group using a greedy approach. For each group, the strategy is to remove all but one balloon, specifically retaining the balloon with the highest removal cost. This ensures that the overall removal cost is minimized. The cost for removing the other balloons in the group is calculated as the total cost of the group minus the maximum removal cost within that group. This value is then added to total time. After processing a group, the pointer I is advanced to the next unprocessed balloon, ensuring we continue traversing the rope efficiently. When the entire rope has been processed, the algorithm simply returns the accumulated total time, which represents the minimum cost to make the rope colorful. The greedy approach is particularly effective here, as it ensures we always make the optimal choice at each step, retaining the balloon with the highest removal cost within each group. This minimizes the overall cost while satisfying the problem's constraints. Consecutive balloons with the same color naturally form groups that can be processed independently, simplifying the logic. The algorithm is efficient, processing each balloon exactly once, which gives it a time complexity of O(n), where n is the length of the rope. Additionally, it operates in constant space, O(1), as it only requires a few variables for calculations, such as the pointer and the cumulative cost. The needed time array provides quick access to each balloon's removal cost, and a single pointer is sufficient to traverse the string of colors. These factors make the algorithm both efficient and easy to implement. Let's go through a detailed example to understand the algorithm step by step. Suppose the input consists of colors equals abg and needed time equals 1, 2, 3, 4, 5, 6. First, we initialize total time to 0 and set the pointer I to 0. We then process the first group, which consists of the two balloons. The costs for this group are 1, 2, with a maximum cost of 2 and a total group cost of 1 plus 2 is equal to 3. To retain the balloon with the highest cost, we remove the others, incurring a removal cost of 3 minus 2 is equal to 1. This value is added to total time, and the pointer is updated to the next unprocessed position, which is 2. By systematically calculating and updating these values, we ensure the solution remains both correct and efficient. Next, we process the second group, consisting of the two B balloons. The costs for this group are 3, 4, with a maximum cost of 4 and a total group cost of 3 plus 4 is equal to 7. The removal cost for this group is 7 minus 4 is equal to 3, which is added to total time. The pointer then moves to the next unprocessed position at index 4. Finally, we process the third group, the two C balloons, with costs 5, 6. Here, the maximum cost is 6, and the total group cost is 5 plus 6 is equal to 11. The removal cost is 11 minus 6 is equal to 5, which is added to total time. With all groups processed, the final total time becomes 1 plus 3 plus 5 is equal to 9. This value is returned as the minimum cost to make the rope colorful. Several edge cases are worth noting. If all balloons have unique colors, no removal is needed, and the total time remains 0. Conversely, if all balloons share the same color, we would remove all but the one with the highest removal cost. For a single balloon, no removal is required since there are no adjacent balloons to consider. The algorithm's efficiency is further enhanced by its greedy approach, ensuring that each balloon is processed only once. By using a single pointer and direct array access, the algorithm minimizes memory overhead. This combination of simplicity and efficiency makes the solution robust, scalable, and capable of handling large inputs effectively while addressing all potential edge cases. This Python solution minimizes the time required to make the rope colorful by ensuring no two adjacent balloons have the same color. The minCost function takes two arguments: colors, a string where each character represents the color of a balloon, and needed time, a list of integers where each value represents the time required to remove the corresponding balloon. The algorithm begins by initializing total_time to 0 to keep track of the total removal cost. It uses a variable I to traverse the colors string. A while loop iterates through the string, grouping consecutive balloons of the same color. For each group, it calculates the sum_time, total removal cost for the group, and determines the max_time, cost of the most expensive balloon in the group. The key idea is to remove all balloons in the group except the one with the highest cost. This is achieved by adding sum_time, max_time to total_time. Finally, the algorithm moves to the next group by setting I to j, where j is the index after the current group. The algorithm ensures all edge cases are handled, including ropes with no repeated colors, ropes where all balloons are the same color, and mixed cases. Its time complexity is O(n), as it processes each balloon once, and its space complexity is O(1), since it uses only a few variables for computation. Here, we are implementing the solution in Java. The method minCost takes two inputs: a string colors representing the rope's colors and an integer array needed time that indicates the time required to remove each balloon. First, we initialize total time to 0, which will store the total time required to make the rope colorful, and I to 0 to serve as our loop index. The main logic begins with a while loop that iterates over the rope. Inside the loop, we create a variable j to explore groups of balloons with the same color, and we initialize two additional variables: max time to track the maximum removal time within the current group and some time to accumulate the total time for all balloons in the group. Next, we use a nested while loop to group balloons of the same color. This loop continues while the current balloon j has the same color as the starting balloon I. For each balloon in the group, we add its removal time to some time and update max time if the current balloon's removal time is the largest we've seen so far. Once we've processed all balloons in the group, we calculate the time required to remove all but the most expensive balloon by subtracting max time from some time, and we add this value to total time. Finally, we update I to j to move to the next group of balloons. After processing all the groups of balloons, the method returns total time, which represents the minimum time required to make the rope colorful. By ensuring that we only remove the least expensive balloons in each group, this implementation achieves the desired result efficiently. The use of a single pass through the rope, combined with the nested loop to process groups of the same color, ensures that the solution is both time efficient and straightforward to understand. To solve this problem, we start by initializing total_time to 0, which keeps track of the total time needed to make the rope colorful. We also set I to 0, as this will help us traverse through the colors array. Now, for the first group of balloons with the color A, we set up j to start at the same position as I, and initialize max_time and some_time to 0. As we process balloon 0, we add its needed time value of 1 to some_time, making it 1, and update max_time to the greater value between the current max_time and needed time, 0, which is also 1. After this, j is increment to 1. Since the next balloon has a different color, we exit the loop. To make this group colorful, we remove all but the most expensive balloon, which means subtracting max_time from sum_time. However, since this group already has only one balloon, the contribution to total_time remains 0. Finally, we move the pointer I to the next balloon to continue processing. For the next group of balloons with the color B, we repeat the process. Starting at balloon 1, we initialize j, max_time, and sum_time to 0. We then process balloon 1 by adding its needed time value of 2 to sum_time, making it 2, and updating max_time to 2, as it is the larger value. After this, j is increment to 2. Since the next balloon has a different color, we exit the loop. Again, there is only one balloon in this group, so total_time remains unchanged at 0. Moving on to the third group, which consists of two consecutive balloons with the color A, we begin by resetting j, max_time, and sum_time to 0. Balloon 2 adds its needed time of 3 to sum_time, making it 3, and updates max_time to 3. Balloon 3 then adds its needed time of 4 to sum_time, updating it to 7, and updates max_time to 4, as it is the larger value. At this point, j is increment to 4. Since the next balloon has a different color, we exit the loop for this group. Now, to ensure the rope remains colorful, we remove all but the most expensive balloon. This means subtracting max_time from sum_time, which gives 7 minus 4 is equal to 3. We add this value to total_time, updating it to 3. Moving on to the fourth group, which contains only one balloon with the color C, we again reset j, max_time, and sum_time to 0. Balloon 4 adds its needed time of 5 to sum_time, making it 5, and updates max_time to 5. Since there are no more balloons to process, we exit the loop. For this group, removing all but the most expensive balloon results in no change to total_time, as sum_time and max_time are the same. Thus, the final value of total_time is 3, which is our output for this example. In this example, we are given the input colors equals and needed time equals 1, 2, 1, 2, 1, 2. We begin by initializing total_time to 0 and I to 0. For the first group of balloons, which consists of two consecutive balloons, we start with j, max_time, and sum_time set to 0. Balloon 0 adds its needed time of 1 to sum_time, making it 1, and updates max_time to 1. Then, balloon 1 adds its needed time of 2 to sum_time, updating it to 3, and updates max_time to 2. At this point, j is increment to 2. To make this group colorful, we remove all but the most expensive balloon by subtracting max_time from sum_time, resulting in 1 being added to total_time. We then proceed to the next group. For the second group of balloons, which consists of two consecutive B balloons, we follow the same process. After processing these balloons, the contribution to total_time increases by 1, making it 2. Next, for the third group, which consists of two consecutive C balloons, we again follow the same steps. After processing these balloons, the contribution to total_time increases by an additional 1, bringing the total to 3. Finally, after processing all groups, the total time needed to make the rope colorful is 3, which is our output for this example. In this example, the input consists of a single balloon with colors equals A and needed time equals 10. We initialize total_time to 0 and I to 0. Since there is only one balloon, it forms its own group. Starting with j, max_time, and sum_time set to 0, we process balloon 0 by adding its needed time of 10 to sum_time, making it 10, and updating max_time to 10. As there are no more balloons to process, we exit the loop. The total time spent on this group is calculated by subtracting max_time from sum_time, but since they are equal, the contribution to total_time is 0. With no further groups to process, the total time needed to make the rope colorful remains 0. This is our final output for this example, as no further adjustments are required when there is only one balloon in the input. To analyze the time complexity of the solution, we start with the outer while loop. This loop iterates through the string colors using the variable I. At each step, I advances to the end of a group of contiguous balloons that share the same color, ensuring that each position in the string is visited exactly once. As a result, the total number of iterations for the outer loop is proportional to the length of the string, denoted as n. Next, we have the inner while loop, which processes each group of contiguous balloons. This loop uses another variable, j, to traverse through the group, computing the total removal time for all balloons in the group and identifying the maximum removal time within it. Importantly, since I and j do not revisit any index, the inner loop also contributes at most n iterations over the course of the entire algorithm. Together, these loops ensure that the solution traverses the input string linearly. Now, focusing on the operations within the inner loop, each iteration performs constant time computations. These include updating the sum_time, finding the max_time, and incrementing the pointer j. Since these are all O1 operations, they do not add additional complexity. When we combine the contributions from the outer and inner loops, both of which traverse the input string linearly, the total time complexity becomes O(n). This holds true across all scenarios. In the best case, where all balloons have different colors, each balloon is processed once, and in the worst case, where all balloons share the same color, the entire string is considered as one group. Regardless of groupings, each balloon is visited exactly once, solidifying the time complexity as O(n) for all cases. Turning to space complexity, the memory usage of the solution is primarily determined by the input. The string's colors and the array needed time together require O(n) space, where n is the length of the input. Beyond this, the algorithm uses a few auxiliary variables, such as total_time, I, j, sum_time, and max_time. These are scalar variables and collectively require constant space, or O(1). Importantly, the solution does not rely on any additional data structures, such as lists, stacks, or hash maps, which means no extra memory is allocated. Therefore, when combining the input space and the constant auxiliary space, the total space complexity is O(n). Finally, let's compare this solution to a naive approach. A brute force solution might involve evaluating every possible subset of the needed time array to determine which balloons to remove, leading to an exponential time complexity of O(2 to the power of n). This is highly inefficient for larger inputs. The optimized solution avoids this by adopting a greedy algorithm. Instead of considering all possible subsets, it processes each group of balloons with the same color in a single pass. By keeping the balloon with the highest removal time and removing the others, it minimizes the total removal time efficiently. Mathematically, this optimization ensures that each balloon is processed exactly once, resulting in a linear time complexity of O(n). Similarly, since the space usage is dominated by the input, the space complexity remains O(n). When solving this problem, there are several common mistakes to watch out for. First, some solutions fail to account for the order of balloons when minimizing costs. Simply summing the costs of adjacent balloons of the same color is not enough. You need to ensure that the balloon with the highest cost in each group is preserved, as this minimizes the total removal cost. Next, overcomplicating the solution with extra data structures, like additional arrays or hash maps, is another frequent error. This increases space complexity unnecessarily, as the problem can be solved using a greedy approach with O(1) space. Another area where mistakes happen is skipping edge cases. For instance, if the string has no repeating colors, such as ABC, or if all balloons are the same color, like AAA, these scenarios must be handled correctly to avoid runtime errors or inaccurate results. Finally, inefficient implementations, such as using nested loops to check all adjacent pairs repeatedly, can lead to O(n²) time complexity, which is too slow for large inputs. A single pass through the string is enough when done carefully. Another challenge is correctly handling the last group of balloons. If the end of the string is not handled properly, you might miss accounting for the cost of the final group of repeated balloons, leading to incomplete results. Now, let's focus on some key insights for interviews. The essence of this problem is to identify groups of adjacent balloons with the same color and systematically remove the ones with the smallest costs in each group, while keeping the highest cost balloon. This boils down to a classic greedy algorithm, where making locally optimal decisions by removing the smaller cost balloons leads to the globally optimal solution. To achieve this efficiently, aim for O(n) time complexity with O(1) space by iterating through the string once and maintaining a running sum of costs. Before jumping into coding, clarify any doubts with the interviewer, like whether the input always contains at least one balloon or if the cost array length is guaranteed to match the string length. This ensures your solution is robust and handles all valid inputs correctly. To deepen your understanding, it's helpful to look at related problems. For instance, LeetCode 409, Longest Palindrome, also focuses on grouping characters to achieve a certain condition, much like how we group balloons by color here. Another example is LeetCode 134, Gas Station, which is a greedy problem requiring local optimal decisions to achieve a global solution. Similarly, LeetCode 55, Jump Game, demonstrates how greedy algorithms can identify the optimal path in linear time. Lastly, LeetCode 1007, Minimum Domino Rotations for Equal Row, involves minimizing operations to achieve uniformity, akin to minimizing balloon removal costs in this problem. Now, let's consider alternative approaches. A brute force solution would involve iterating over all possible removal sequences to find the one with the minimum cost. While this guarantees correctness, it's highly inefficient, with a time complexity of n squared, or worse, making it impractical for larger inputs. On the other hand, the greedy approach, which involves traversing the string and tracking groups of repeated colors, is optimal. It ensures n time and 1 space complexity, making it the best choice for this problem with no significant downsides. Another approach to consider is dynamic programming. Here, you could use a DP table to track the minimum cost required to make the rope colorful up to each index. While this guarantees correctness, it comes with the trade-off of increased space complexity, specifically, n, which is unnecessary given that the greedy solution already solves the problem efficiently. Since the greedy approach provides both optimal time and space complexity, there's usually no need to rely on dynamic programming here. By focusing on the simpler and more efficient solution, you can save both time and resources while still achieving the correct result. Great job! To wrap up, we reviewed the key algorithm and its complexity for solving this problem. Remember, greedy algorithms are a powerful tool for optimization challenges. Thanks for joining, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!